In this video, I'm going to take a look at how you work out the shapes of simple molecules and ions. So simple molecules form when atoms are covalently bonded, and so we're talking about things like carbon dioxide, ammonia, the ammonium ion, H2O, that sort of thing. We're not talking about ionic substances, and we're not talking about giant covalent substances. So just simple molecules. So the absolute fundamental thing we need to know to work out the shape is the number of electron regions that are in the valence shell of the simple molecule. So what do I mean by that? Well, there's a very simple dot and cross diagram of the methane molecule, CH4, and the electron regions in the valence shell are these, in this case, electron pairs around the carbon. So you can see we've got 4 electron regions in that valence shell, and they are going to determine the shape and the angle between the H, the C and the H in this case. So we'll just quickly talk about the types of electron regions you can have. So you can see I've got 2 sort of key regions here. So the first type are the bonding regions. So obviously that's what we've got here. We've got single covalent bonds, 1 pair of electrons, where the carbon and the hydrogen have supplied an electron each. We can also have multiple covalent bonds. They're also classed as bonding regions, obviously. And you can also have dative covalent bonds, or you might be more familiar with them as coordinate bonds. You can also have lone pairs. They will also influence the shape and the angle in the molecule. So the last thing I need to say on this introductory board is, well, what do these electron regions do? Well, they're all negatively charged because they're all made from electrons. So what are they going to do? They are going to repel each other, and they want to get as far apart as possible. And what you're going to see in the video is the number and type of electron regions is going to dictate the shape and the angle. Okay, so we're going to start looking at some examples now, and the way I'm going to organize the video is I'm going to start with bonding regions only. So it's going to be the first section of the video. Then I'm going to move on to what if there's lone pairs in the valence shell, and then the final part of the video I'm going to look at ions. So the first one we're going to look at is where you've got 2 bonding regions only in that valence shell, and the example I'm using is carbon dioxide. So you can see I've already drawn up the dot and cross diagram. It's always a good idea to have a dot and cross diagram so you can actually see the numbers of regions, the electron regions in that valence shell. So we've got double bonds between the carbon and the oxygens, and you can see I've written up there multiple bonds count as 1 region. Now there are very, very few examples of 2 bonding regions where you've just got single bonds here. So that's why I'm starting with this one. So all we're interested in is this part here, and you can clearly see we've got 2 electron regions, 2 bonding regions. They're going to repel each other and try and get as far apart as possible. And obviously the furthest apart they can get is 180 degrees. And so the shape, well, there's a model of a carbon dioxide molecule. Everything's in a straight line. So this is known as a linear molecule. So if you were asked to draw a diagram of the shape of the carbon dioxide molecule, you'd draw something like this, okay? So everything in a straight line. Obviously the double line represents the double covalent bond. We've got the name there, linear, and the angle between the oxygen, the carbon and the oxygen is 180 degrees. So that's what we would call the bond angle. The other example I've got for this scenario of 2 bonding regions in the valence shell is hydrogen cyanide. So again, I've started with a dot and cross diagram. You can see we've got a single covalent bond between the hydrogen and the carbon. So that's where each atom just puts 1 electron into the shared part. On this side, each atom's putting 3 electrons in. So we've got a triple covalent bond here. But remember this rule, multiple bonds count as 1 region. So we've still only got 2 bonding regions. So this is also going to be a linear molecule with a bond angle of 180 degrees. And there's the model. So you can see everything's in a straight line. And there's the bonding diagram. So we've got the H to C single bond, the C triple bond N It's a linear molecule, 180 degree bond angle. So moving on to 3 bonding regions in the valence shell, we've got this example here, BH3, boron trihydride, and you can see again, I'm starting with my dot and cross diagram. You can see we've got 3 single covalent bonds, so we've got 3 bonding regions, and these are going to all repel each other in such a way that they get as far apart as possible, and the shape that they adopt is, well, there's a model of the BH3 molecule. So you can see that everything is in the same plane. So it's a flat molecule, so we call it a planar molecule. And because we've got this triangular shape here, we call it trigonal planar. So there's the shape diagram there. There's a couple of extra points I need to make here. So we've got these solid lines representing the single covalent bond between the boron and the hydrogen. And the fact that it's a solid line, you'll see what I mean by this when we get into the next scenario where we've got 4 bonding regions. This type of bond drawn like this means that everything is in the plane of what it's been written on. So in my case, it's the whiteboard. In your case, it would be your notes or your exam paper, whatever you're writing on. So these bonds are all in the plane of the surface that you're writing on. There's the angle. Obviously, it's 120 degrees between all of them, but I'm just showing that one there, 120 degrees, and there's your shape, trigonal planar. So moving on to 4 bonding regions now. So we've got the CH4 molecule is going to be our example. There's my dot and cross diagram. You can clearly see you've got 4 single covalent bonds between the carbons and the hydrogens. And at first glance, you might be thinking that the angle is going to be 90 degrees, and you're going to get sort of like a cross shape, a square shape. Now that's not actually the case, because what happens is if it forms a 3-dimensional shape, it can actually maximize the distance apart between the electron regions, the bonding regions. And the shape it adopts looks like that. So I'll just hold it up and show you. So this is what we call a tetrahedral shape. And the angle, now don't worry about this number, you don't need to know where it comes from, you just need to remember it. So this angle here is slightly more than 90 degrees, so 90 would be like that, wouldn't it? So it's slightly more than 90 degrees, it's actually 109.5 degree bond angle between the hydrogen, the carbon and the neighbouring hydrogen. They're all the same, by the way, but I'm just focusing on that one there. So how would we draw this? Well, this is where it starts to get a little bit trickier. So what I'm going to do is I'm going to pull these 2 bonds off for the moment, and I'm just going to lie that flat on the whiteboard. So you can see there, those 2 bonds are in the same plane. So remember what I said about the bond type, the way you draw it. So I'll draw it side by side. So we've got carbon there. So we've got this bond straight up, the way I've positioned that. And I always draw them like this. So we've got a bond in the plane going straight up, another bond in the same plane going sort of at that angle there. So just try and make sure that that angle looks more than 90. So you don't want to be doing that, a right angle. So a bit more than 90. Okay, so now let's put this 3rd bond on, and you can see that it's sticking out of the plane. So how do we show that in a diagram like this? Well, we draw a wedge. So you can either leave it unshaded like that, or you can shade it in, it's up to you. Put the hydrogen on the end. So this bond here is coming out of the plane, out of the whiteboard, out of the notes that you're writing in. And then the final bond, I'm going to have to pick up the molecule now, the model. Okay, I can't lie it flat anymore because obviously that bond's poking down that way. So how do I show a bond that's going behind the plane? We draw either a dashed wedge or just a dotted line. I'll just go for a dotted line. So this bond here means it's going down behind the plane. So that kind of gives it a bit of a 3D perspective. All of these angles are the same, 109.5 degrees. So I'll just label that one up, 109.5 degrees. Remember, don't worry about where the number comes from. It's just that is the angle, the furthest apart that these regions can get. And the shape is tetrahedral. So moving on to 5 bonding regions now. So the example I'm using is PCl5, phosphorus pentachloride. Again, there's my dot and cross diagram to start with, and you can see we've got 5 single covalent bonds between the phosphorus and these chlorines. So I'll just bring the model straight into play. There it is there. So that is the shape, or that's the furthest apart that these 5 bonding regions, electron regions, can get. And we'll talk about how to draw this now. So like I did with methane, I've taken off the bonds that are not in the plane. So I've left 3 on, and we'll start drawing the molecule. So I need a central P. You can see this bond's going straight up. It's in the plane, so I use this type of line. So Cl, that's in the plane, so Cl, and that's in the plane, so Cl. So if I put the 4th bond on, like I did with methane, and put that one on there, so that's now sticking out. So remember, we use a shaded wedge to represent that. It could be unshaded, sorry, as well, but I tend to do shaded ones. So we've got that there. And again, I'm going to have to pick it up now and put the final bond on. I can't lie it flat anymore because that bond's sort of hitting the board. Again, we just dotted line means that that bond's going behind the plane Cl. So that's how you would draw that. So the shape, what's that called? It's called trigonal bipyramidal, or a trigonal bipyramid. So we'll just finish by talking about the angles between the atoms. So in a trigonal bipyramid, you've got 2 angles effectively. So we've got this angle here. So this one, this one, this one, and then on the bottom as well. And they're all, hopefully you can appreciate, 90 degrees. So I'll just mark that one up. So that's 90 degrees. And then the other angle we've got is around the middle. So you've got this angle here. And obviously that's the same, that's the same. So I'm talking about these angles around here. So I'll put, which one should I put on? That one there. That's 120 degrees. And finally, in this section where we're just looking at bonding regions only, we've got 6 bonding regions, and the example is SF6 sulfur hexafluoride. There's the dot and cross diagram, and you can see we've got 6 single covalent bonds, 6 electron regions in this valence shell here. So in terms of shape, we get this here. So this is what we call an octahedral shape. So where does the 8 come from when we've just got 6 regions, 6 atoms around the central sulfur? It's down to the number of faces we've got. So if my hand there represents a face on the shape, so 1, 2, 3, 4, and then another 4 on the bottom. So 8 faces is where octahedral comes from. So in terms of drawing this, well, you can see I've got 4 bonds here that are all in the plane of the whiteboard. The only problem is if we draw the diagram starting with that, it's very difficult to show a bond that's sticking straight out and straight back. So rather than do that, I'm going to take these bonds off as well, and that's going to be my starting point. So we've got an S with an F straight up and an F straight down. So the next thing I want to do is I'm just going to rotate that around. It's still flat to the board, but I've now got 2 bonds that are sticking out like that, which means that what I'm going to do is I'm going to draw 2 wedges to show we've got these 2 bonds coming out of the plane. Put the fluorines on, and then same on the bottom, but obviously I've got to pick it up now, put them on the back. We've got the 2 bonds coming out, we've got the 2 bonds going back, which means that I'm going to draw 2 dashed lines there and there. Sorry, that's not very straight, but there you go. Right, angles wise, well, all the angles are the same. If I just pick up the model, you can see all the angles are the same, and they're all 90 degrees. So I could pick any one of these. I'll go for that one, 90 degrees. And shape-wise, octahedral. So for the next section of the video, we're going to start looking at the impact of the presence of lone pairs in the valence shell. So the fundamental thing, the most important thing to appreciate is repulsion will no longer be equal. So in all the examples you've seen so far, where you've just got bonding regions, the repulsion between those electron regions has been equal. It's not the case when you've got lone pairs. The reason for that is beyond A-level chemistry, but if you are interested, it's because lone pair orbitals are shorter and rounder than bonding pair orbitals, and they basically can repel more than bonding regions. But there's a specific order that we need to be aware of. So in the box there, we've got the repulsion order. So the strongest type of repulsion is between two lone pairs. Then we've got the lone pair to bonding pair repulsion. And then finally, the weakest type of repulsion is what we've seen so far, bonding pair to bonding pair. So on something like SF6, that's what we've got. Bonding pair to bonding pair repulsion, that's the weakest type. So the examples I'm going to use for this section of the video will incorporate these two scenarios. So the first example I'm going to look at is the ammonia molecule, NH3. Again, there's my starting point, my dot and cross diagram, and you can clearly see we've got 3 bonding regions and we've got 1 lone pair. So the repulsion won't be equal in this molecule. Now, fundamentally, we've got a total of 4 electron regions. So the number of electron regions is going to dictate the sort of the initial shape, the initial bond angle between the regions. And remember what we said for 4 bonding regions, we had the tetrahedral molecule, the tetrahedral shape. So there's my methane model. So it's going to be like this, but there is a slight difference. So there is my model of the ammonia molecule. So obviously this represents here the bonding region between the nitrogen and the hydrogen. This brown circle here, the sphere, is the lone pair. You see it's sitting a lot closer to the nitrogen than these do. So you can see what I've done here, and it's really important that you do this. Once you've established the total number of electron regions you've got, we now need to break it down into the types. So we've got 3 bonding regions, and we've got 1 lone pair. And because we've got the different types of regions, electron regions, we need to say that the repulsion isn't equal, and that's because lone pair to bonding region, so this to this, is greater than bonding region to bonding region, so these regions here. So I'll just pick this up and show you the effect of that. So the starting angle, remember for 4 regions when they were all bonding regions, was 109.5, but this repulsion here is slightly stronger than this repulsion here. And what it does, if I can just hold this in position, I'm just going to squeeze the hydrogens a little bit closer together to represent this extra repulsion from between the lone pair and the bonding region. So it's going to squeeze these slightly closer together, and the rule of thumb is for a lone pair, for 1 lone pair, we're going to reduce the angle by 2.5 degrees. So in this, it's 109.5. So in this angle will be 2.5 degrees less than that. So it's going to be 107. Now in terms of the shape, we're not calling it a tetrahedral shape because we haven't got 4 atoms sort of bonded to the central atom. We've only got 3. So it gets a bit tricky, and as a teacher I do see confusion in students' sort of answers because they kind of bring in, they're saying it's tetrahedral and it isn't. We call this pyramidal, okay? So all we're counting for the shape are the atoms. So we've got 3 atoms, so this is called a pyramidal shape. So if we look at how to draw this now, so remember our sort of starting shape is a tetrahedron, but it's pyramidal because of the 3 atoms and not the 4. So if you remember how you drew the tetrahedron before, you've got 2 bonds in the plane. Okay, so what I always do, it's the way I was taught to do this, and I've stuck with it, I make the lone pair one of the bonds in the plane. I always make it the one at the top there. Okay, so then my other bond is the other bond in the plane, which means that I have a bond sticking out. So just shade that in, but remember you don't have to shade it in. And we have a bond going back. So that is how you draw the pyramidal shape, and the angle, all of the angles are 107 degrees. So the second example I'm looking at where we've got lone pairs present is H2O. So we've got the dot and cross diagram there, and you can see we've still got 4 electron regions in total. 1, 2, 3, 4. But this time we've got 2 bonding regions. We've got 2 HO bonds, and we've also got 2 lone pairs. So again, the repulsion's not equal, and there's the complete repulsion order. So we've got lone pair to lone pair. Obviously, they're going to repel each other. That's greater than lone pair to bonding region. So that repels that, that repels that. And then bonding region to bonding region, they're repelling each other as well. So there is the model of the H2O molecule. So you've got your 2 bonding regions, your 2 lone pairs. So if I just pick it up and just squeeze the hydrogens together, because we've got 2 lone pairs now, we take 5 degrees off the starting angle. So the starting angle is going to be 109.5 from the fact that we've got 4 regions, but we're going to take 5 degrees off now because of this double lone pair repulsion here. So the angle will go down, this angle here will go to 104.5. So if we move on to how to draw this now, remember our starting shape is the tetrahedral arrangement, but this is not a tetrahedron because we've only got 2 atoms bonded to the oxygen. But just sort of think about how we drew the tetrahedron before. So central oxygen, and we've got 2 bonds in the plane, and then we've got the wedge and the dashed line. So if you make those the hydrogens, obviously they're going to be your lone pairs, and then just sort of spin that round so that it looks like a normal molecule, if you like, and we've got that there. So this angle here is the 104.5 degrees. What do we call that shape? Well, it's just called non-linear. So obviously this hydrogen is not in a straight line, it's on this angle here, so it's classed as non-linear. You could also call it bent, you could also call it V-shaped. They're all accepted names for this. So the third and final example I'm going to look at in this presence of lone pairs section is sulfur dioxide. So again, dot and cross diagram to start with. You can see we've got 3 electron regions. We've got 2 of them are bonding regions. These are double covalent bonds, but remember that doesn't matter because it's still just classed as 1 region. So 2 bonding regions, 1 lone pair. Repulsion won't be equal because the lone pair to bonding region repulsion is greater than bonding region to bonding region. So in terms of shape, well, there's the model of the molecule itself. So our starting angle is going to be based around the fact that we've got 3 regions. So remember, it was 120 degrees is the starting angle for 3 regions, but we've got this extra repulsion from the lone pair to the bonding region. So again, I'll just pick that up and just squeeze it slightly closer together. So it's going to knock 2.5 degrees from that. So the angle is going to be 117.5 degrees. So in terms of shape now, well, it's based on a trigonal planar shape, but it won't be classed as trigonal planar because we've only got 2 atoms bonded to the sulfur. So we've got, everything's in the same plane. So we're just going to draw these double covalent bonds to the oxygen angled. Obviously the lone pair we can put up here, and there's that angle, 117.5 degrees. And again, it's not a straight line, it's slightly off, so it's a non-linear shape. But you could say V-shaped as well. So moving into the final section of the video now, where we're going to look at simple ions. I'm just going to look at these 2 examples and hopefully it'll all make sense from that. So we're going to look at the ammonium ion, NH4 1+, and the sulfate ion, SO4 2-. So dot and cross diagram to start with. So what have we got around the nitrogen? We've got 4 electron regions. They're all bonding regions. Now we've got 3 regular single covalent bonds, and we've got this dative covalent bond where the nitrogen's providing both of the electrons to this, which was an H+ ion. So we've got a dative covalent bond, a coordinate bond here, and the whole thing's now carrying that positive charge. but effectively we've just got 4 bonding regions, and so it's going to just be tetrahedral with the angle of 109.5 degrees between all of the atoms. So there's my shape diagram. So just a classic tetrahedral shape. That bond there, remember that's the coordinate bond or the dative covalent bond. So that's represented as an arrow because it's showing the direction the electrons are coming from. So they're coming from the nitrogen to the H plus ion. So it's drawn that way. 109.5 degree bond angle, obviously tetrahedral shape. And finally the sulfate ion. So there's my dot and cross diagram. So you can see we've got double covalent bonds between this sulfur and this oxygen and this one. And here we've got single covalent bonds, and I've needed to bring in a third shape for electrons. So I've got a triangle there to show the extra 2 electrons that's given at the 2- charge. But fundamentally we've got 4 bonding regions, so we're going to have equal repulsion, and again this is going to be tetrahedral with a 109.5 degree angle. So I'll just draw up the shape diagram and that's it. So there's my shape diagram there. I'm not wrapping this one in a bracket and having a 2- charge because I want to just show that the minus signs, the minus charges, are on these singly bonded oxygens. And again you'll notice that I've put the double bonds in the plane, just makes it easy to draw than trying to draw a sort of wedge shaped double bond and dashed line version as well. So double bonds in the plane, so the single bonds are sticking out and going back. So to finish, I just thought I'd go through a list of essential things you've got to include in any answer about shapes of molecules or ions. So the first thing obviously you've got to do is establish the total number of electron regions in the valence shell. Once you've done that, say what types and how many of each type of electron region you've got. So maybe they're all bonding regions, or you've got a mixture of bonding and lone. So say how many of each type you've got. Once you've done that, you need to make a statement about repulsion. So is it going to be equal? If you've got all bonding regions, it's going to be equal. If you've got a mixture of bonding and lone, it's going to be unequal. And if you have got unequal repulsion, say why it's not equal. So you get your statement about your repulsion order in there. And then finally, obviously there's an associated shape and angle with any set of regions. So you would draw that out, get the angle drawn in, and you would get full marks. Okay, so that's it. I hope that was helpful. Let me know what you think in the comment section. And yeah, best of luck with your shapes of molecules questions.